Welcome to module 42 of Database Management Systems course in IIT Madras online BSc program. In the last module, we have introduced the concept of indexing and the need for that, and we understood the fundamentals of ordered indices, primary index, secondary index, dense index, sparse index, multi-level index and all that. Now, before we move further, we would again like to step back a little, because the next that we want to understand is to be able to implement these indices and the actual index sequential access method, what kind of external structure in the disk we have to create, which happens to be B tree or B plus tree, which will be efficient as an external structure catering to the basic requirement of my database relation data as well as my index tables. So, in this module, I again step back a little. I developed this concept from the in-memory data structure that we have seen, extend them to a point where they can be directly extended or actually kind of replicated in a external disk mechanism. So, that is what we will discuss today. We will talk a little bit more about balanced binary search tree and specifically 2, 3, 4 trees. Now, we have talked about binary search trees. You know this pretty well, linear search, all these you know, order n, binary search, order log n if it is sorted, and we saw that this can be actually mimicked in a nonlinear data structure, binary search tree, where the search could be really made efficient in terms of going through the comparison over this binary tree. And once the search is efficient, then the insertion or deletion can also be done efficiently by manipulating a few pointers. Right. So, that is what we have learnt at the fundamental level, and this is what we have seen the trade off between different of these, and this is the key result that we have come to learn is binaries. In a binary search tree, the search is order h, order height, given the fact that the height is between these ranges. And once you have been able to search, then in additional order one time you can do an insert and delete. Now, the point is, if you as you see the bounds on h, you have noted this earlier also, that if you are not careful, then a binary search tree, the height of a binary search tree could tend to become n. If it becomes n, then since this is order h, we lose all the advantages of doing a conceptual binary search. We will fall to order n. So, we have to do something to make sure, as we keep on doing different inserts and deletes, the height of the tree remains of the order of log n. Okay? And if we can ensure that, guarantee that, then we say that the binary tree is balanced. So, again, just to recap, this is your basic fundamental result, that the search key in the worst case in a BST will be searched in order h time. Trees may be bad where we have order n, and trees may be good where we have order log n. Right. This we specifically, this slide we discussed in the module we were discussing this. I just replicate it so that the whole thing stays in your mind. So, the question is how to only work with good trees that will remain balanced. Now, in this we kind of note, though we will not go deeper into this, that balancing is about giving a guarantee. You want this. Now, the question is, what are the ways you can guarantee that the height will be of the order of log n? And there are different guarantee strategies that have been worked out, that have happened. One is called the worst case guarantee. which is what we have learned from the complexity of the algorithms, that in the worst case this must be guaranteed. So, which is the set of self-balancing BSTs, primary being the AVL tree, which is also the oldest of these data structures, which ensures that the height of two subtrees of a node, if you take any node, the height of the two subtrees that are rooted at this node, the children of the node, you have a node, you have two children left and right, and you have two subtrees, a left subtree and right subtree, having height h, l and h r. At every node, these heights of the left and right subtrees must not differ by more than 1. If they differ by more than 1, because you have entered, you have inserted, the difference was 1 and you have inserted a key at the leaf node, so that height has increased, then you have to do some rebalancing, and there is a whole lot of strategy by which you can rotate a tree and balance it. This is not an algorithms course, so we will not get into this, but there is a different variants of this self-balancing BST, which guarantee that you will always have the worst case, always have h be of the order of log n in the worst case. It will be good to have that, but it has a lot of costs as well. In actual terms, first of all, doing these rotations are non-trivial, and the actual cost of rotation in the physical runtime could be quite a lot. There is a lot of overhead and so on. So comes a very different concept, which is from the domain of randomized algorithms. Some of these are getting implemented in database context also, but I am currently talking only from the algorithms context. So, which gives rise to say, okay, why did we get bad trees? Because we kept on possibly inserting in a particular path. Right. Now, how do we get a good tree? If without doing anything, without doing AVL or anything, how can I get a good tree? I can get a good tree because if my data is purely random. If my data is purely random, then when I am inserting, there is an equal probability of the data to go to the left child or to go to the right child, recursively at any level of the tree. If that happens always, then I am doing equal amount of insert on the left and right subtree of the entire tree at every node, which automatically guarantees that from leaf upwards every subtree is balanced, and if every subtree is balanced, the whole tree is balanced, it is order log n. Right? But the fact of the matter is that most often the data is biased, it is not random. So, if we just follow the data in the order in which it comes, I cannot get a balanced binary search tree. So, that is where this beautiful concept of randomized BST comes, which says that turn the table around. The data may be biased, but what you can do is you can randomly decide which side you will enter it based on the value of the data and certain factors. Right? So, that is, I will not go into the depth. If you study the corresponding book, you will find that this guarantees that the probability of, so you do not talk about a worst case guarantee that h is always order log n, but what you say is the probability of h not being more than order log n is extremely small. So, that is another approach. Another randomized strategy is skip list. I mentioned this, where you keep multiple levels of ordered linked list, much in the way you are doing multi-level indexing. In the bottommost list, you keep all entries. In the second, you keep maybe alternate, half the entries. In the third level, you keep 1/4 of the entries, and so on and so forth. And how you choose which entries to keep at what level, you use a randomization for that, which guarantees actually, if you use a true randomization, it guarantees that it will have an effective search time, which is order log n. Very strictly speaking, I should not be calling this as a binary search tree, because it has a different kind of structure, but it is a linked search structure which follows the binary searching algorithm. So, I prefer to call it that way. And finally, you have splays, which look at the entire Do not look at any specific size, height of the tree or anything. It just says that if I do 10,000 inserts and deletes, then whatever is the cost that I get, if I divide this by 10,000, if that average is order log n, then I am happy. So, that is amortization. So, these are different ways to keep things balanced. Now, the fact of the matter is that these all guarantee order log n, but do they satisfy our requirement now? They are good for in-memory operations. They work well with small volume of data, small compared to what a database needs. They will work well with maybe 10,000, 100,000, 200,000 data, but not with 10 million data, because you cannot fit them in the memory. They have complex rotation or similar operation like randomization, random rotation, all of these, which make it very difficult to scale them up. And consequently, they do not scale, they do not directly map to external data structures. So, this is the state of the art in terms of algorithms in memory data structure, but does not give you as a solution for our database file structure or the database physical structure. So, we look at another data structure which is also in memory called 234 tree, which can give us a very good solution. What is the concept? The concept is we are trying to do something very different in a different approach. What we say is we guarantee or we build the tree in a way that all leaves are at the same level depth. All leaves are at the same depth. So, if all leaves are at the same depth, then naturally the height of the tree has to be log n. Right. That is, but we had observed that all the leaves can be at the leaves provided is n is of the order of 2 to the power h minus 1. And then it will again happen at 2 to the power h plus 1 minus 1. So, what if n is greater than this and less than this within this range? Naturally, you cannot guarantee that all of them will be at the leaf level, because you will not have enough space to keep them, right. Well, so that is the basic challenge. Now, you want to keep the data in sorted order, and that is how you will enter it. So, in the leaf level, if you read it from left to right, it is a sorted order. Right. That is not difficult. The basic question is, where does if n nodes, n data are there, then where does these extra data go in without increasing the height of the tree? Well, very simple. You can let nodes accommodate more than one data values, as long as they satisfy certain properties. So, instead of one node type which we have so far, but the node has only one data value, we create 3 types of nodes. A 2 node which has only one data value and 2 children, 3 node having 2 data values and 3 children, 4 node having 3 data values and 4 children. And the idea is whole thing can generalize to the larger nodes very easily, and therefore, can extend to the external data structure. So, let us look at the concrete proposal. S is a 2 node which has one single data item and 2 search keys like the BST. A 2 node has 2 S and the single and the large, and it has 3. So, these are the data items which are less than S, these are data items which are more than L, and these are data items between S and L. You have to satisfy this. So, this is 2, this is a 3 node having 2 data items, or you can have a 4 node having 3 data items S, M and L. So, that on there are 4 links. The first one is less than L, S, the second one is between S and M here, the third one is between M and L, and the fourth one is L greater than L, right. So, this is how you can create this. You want to have nodes and link them. Now, the rest of the structure is, if you do this, then searching on this will be simple, because you follow the same strategy. You are at a single value, we were checking at a single value earlier, you were checking whether it is less or more and going. Here you will have to check that whether it is less than this, between this, or more than this, and go accordingly. Right? So, the same thing will happen for the phone node. So, search is a natural extension. Now, the question is how do you insert? Now, to insert, you do something very simple. You try to find out by search where your value to insert was expected, like the binary search tree. Right? That is easy to do. Now, what are the possibilities? There are three possibilities. One, that could be a 2 node having one value. If it is a 2 node, you do not do anything, you do not do any going further, linking anything, you just change that 2 node to a 3 node. If it is a 3 node, then you change it to a 4 node. 2 values were there and your new value inserted. So, no height change or anything is required. The question is, if it is a 4 node, then you cannot put more values, because you have assumed that there can be only up to 3 keys in a node maximum. So, what you do of these 3 values S, M and L, you take this out and insert it to its parent, go up, insert it in the parent. When that happens, then you have 2 nodes, 2 values, you put the new value. Subsequent question is, so this is called kind of splitting the node. Now, subsequent question is, what happens in the parent, because you want to insert it there. Now, if there is no parent, you are doing at the root, then you make M the new root. You may have a 2 parent, otherwise you may have a 2 parent, or you may have a 3 parent, right? Because if you are, let us assume that we are not letting a phone node stay by itself when we encounter it. So, up onwards there is no phone node. If there was a phone node, we have already taken care of it, taken its middle value, put to the parent and recursively up to the root. So, it can either be the root itself, it can be a 2 parent node or a 3 parent node. So, what will happen if it is already the 4 node is already the root? Very simple, you split, make M the root, S the left child here, L the right child here, you had ABCD, AB becomes links of S, CD becomes links of L. You please note that you are maintaining the order, because now if anything is between S and M, you will go on this side. If anything is between M and L, you will go this side. And so, therefore, if you have to come to C, what you have is it is more than M and less than L. This is exactly what C was, right, and so on. So, convince yourself that they split. But with this, a 4 node is replaced by 3 2 nodes. If it has a 2 parent, when you, so you have to split this, put this M, put it to the parent. Now, there are 2 possibilities. It can be less than the parent or it can be more than the parent, right. If it is, I am sorry, there are, this is, in this case, the phone node is a left child. So, it is less than the parent, right. Therefore, when I convert this 2 node into a 3 node, it will occur to the left, and then all that I have to do is make S and L the 2 other nodes of this 3 node. E will remain as it is because it is greater than P, there we are not involved. Something between M and P would have been between CD. So, L will point to CD and S will point to AB, because it is less than S or between S and M. Right? So, this converts the 3 node to 1 node at the parent into a 2 node and splits the 4 node. Exactly the similar logic will split it if it is on the right child. And finally, if you have a 3 node as a parent, you just extend that logic. In the left, you take care of it like this. If it is on the middle node, you take care of by putting it in M, and if it is on the right, you take it here. So, in each one of these cases, the 3 node becomes a 4 node. You may choose to propagate to split this, or you may choose to keep it till you come across this 4 node later on. So, with this, what we have guaranteed that in none of these, if I now go back, two steps, then with this insert, a 2 node change to 3 node height did not change, 3 node change to 4 node height did not change, 4 node changed through splitting, and in that splitting, if it becomes a root, then the height changes, but the height changes for all the leaf nodes, because you are changing the height by 1 at the root. So, all paths to all leaf nodes increase by 1. So, H just becomes H plus 1, and it was already everything is filled, at least one node is there in this tree of height H. So, you have 2 to the power H minus 1 or more nodes, therefore, this height cannot be more than log n. This is the only case where your height changes, not like ordinary BSTs where you may change the height almost every time you insert a node. That is the beauty of the 2, 3, 4 tree. If you look into the other cases of split and insert in the parent, the height is not changing. You are just adjusting pointers. You are keeping more space to accommodate more and more nodes, but height is not changing in any of these cases. So, there is only one place where the height changes in a 2, 3, 4 tree, where you split a node, which is a 4 node at the root, and then the height increases. So, by this we come to the conclusion that what we assume that all nodes can be at the same level is possible. Right? So, you could do it do this node splitting by 2 strategies. You can do it early, that is, split a node as soon as you come across it on the traversal, so that when you are going back through an insert, you do not expect any other 4 node to come across. Or it could be a late strategy, that you split a 4 node only when you need to insert an item. There is no trade off, there is no specific trade off between these two, because both finally will add a height when you split the 4 node at the root. Right. Both are valid, have the same complexity. However, these different strategies will produce different results. There could be different trees, but the same performance. For our illustration here, we are following the early strategy. So, quickly an example is in order. So, this is the order in which I want to insert the keys in and make a 2, 3, 4 tree. Right. So, I insert 10, then I get a 1 node at the 2 node at the root, insert 30, this becomes a 3 node, insert 60, this becomes a 4 node. Now, following an early strategy, so when we want to, this has been done, so we want to do insert 20, as soon as we come across this, we have to split. And what do we get in the split is the 30 goes up to the parent, which becomes a new root. So, 30, 10, 60 is the new tree, where I can now insert 20, which I was not able to do in this tree. Right? So, the next step is inserting 20. So, I have inserted 20, it is less than 30 and comes on the left child. Next is to insert 50. So, 50 is greater than this and less than 60. So, it comes on the left. no adjustments needed. I go on, I am inserting 40. As I insert 40, 40 is greater than 50, 30 less than 50. So, it comes here and I have 40 inserted at this point. Great. Now, my next target is to insert 70. If I want to insert 70, then where will it come? Greater than 30, it will come in this phone node, it is greater than 60. So, this is where I have to insert. So, which means I have to split this. So, I split, if I split, middle node goes, middle value goes up. So, this 2 node becomes a 3 node and these 40 comes here separately, 60 comes here separately. Now, we do not have a 4 node, I can easily insert 70, which will come here. Then I have 80, I insert 80, it comes here. Mind you, with all these, at the very beginning after the 3 insertions, the height has changed. In all these, the height is not changing, it remains the same. Now, when I was able to insert 80 and then I have to insert 15, which goes in here, not a problem. I have to insert 90, which has to go here. So, which means this has to split. If this has to split, 70 has to go up. So, it goes up, this becomes a phone node. I have 40, 60, 80 coming as 2 nodes. Right. So, now I am ready to insert 90. So, I have inserted 90 and then I have to insert 100. So, where will 100 go? If I do 100, then it will come here. Right. So, this is now the question is, you may ask as to here the basic point is that I could have on this tree come here and placed 100 here, right. It is possible, but that would mean that I am following a late strategy. Right. So, I will do the splitting next when something pops up from below to cause the root to split, but I am following an early strategy. So, what does that mean? That means that when I am searching for inserting 100, the moment I come across a phone node, I split. So, I split this, as I split this, this becomes the root. These are the 2 children, these are the 2 children. So, again from 1, the height of this tree has now become 2, and then I insert 100. So, my 100 gets inserted here, but on that path there is no phone node. Right. So, this is the basic strategy for 2, 3, 4 tree insertion. You can work out the 2, 3, 4 tree deletion in a similar way. All that you need to do is to whenever whenever you got a phone node and you wanted to insert, you had to remove split and insert in the parent. You will now have to do the reverse, you will have to merge the nodes. Now, so the advantages that we have is all leaves at the same level, complexity of all search is order h, which is log n, data is kept in sorted order. It can be generalized to larger nodes, which is because 2, 3, 4 was just the minimum that you can do, but I can do nodes of a number of types. But certainly it has the disadvantage that I have multiple types of nodes. Right. So, that causes, because I have to always change from a 2 node to a 3 node, 3 node to a phone node to multiple 2 node. So, I have to keep on actually destructing and constructing nodes, which becomes an overhead. So, the strategy could be that we just have phone nodes. We have 3 items and 4 links, and I use it as a 2 node or as a 3 node, and I let some space go west. It is not that kind of a premium. That is the crucial observation here. So, if I have that, that wastage is there. So, leaf node can have 1, 2, 3 items, whatever. Now, this will generalize easily to larger nodes. Again, by the same strategy, all paths from root to leaf are of the same length. Each node that is not a root or a leaf, because at the root we cannot guarantee this, but what we want to guarantee is I have at least half of the things filled up. Otherwise, my wastage will be very, very high. And the leaf node obviously can have number of values which are in this bound. The special case has to be for the leaf, because the tree may not have so many nodes. So, this is the basic idea, that you want to guarantee that all paths from root to leaf are of same length. You want to keep multiple values in the same node, making sure that you have every node at least half filled. So, in case of a 2, 3, 4 tree, n being 4 here, we will make sure that other than the root you must have at least 2 values or 3 values, right? Not, I mean, at least 3 children, 4 children or 3 children, 2 values or 3 values. Right? So, that will make sure that at least more than half the space is always utilized. So, that is that was a foundational idea I wanted to give you, how you transition from an in-memory data structure for search to a external data structure for search. We will develop on this idea more in the next module when we talk about B plus tree and B tree. Thank you very much for your attention, and we will meet in the next module.